Okay, so first of all, let me say a few words about the objects we are going to study and about their history. Well, what is a C-star algebra? Well, first of all, a C-star algebra is an algebra, associative algebra A, over the field of complex numbers. Second, this algebra is equipped with a norm, which makes it into a Banach algebra. And finally, a C-star algebra is equipped with another algebraic operation, the so-called involution, which is a map from A to itself, and which takes each element of A to another element denoted by A star. The involution should satisfy some natural algebraic axioms. In particular, it should be an involution in the set theoretic sense. That is, the square of this operation is the identity map. It should be antilinear, and it is a ring anti-homomorphism. And finally, it is connected with the norm by means of the following important identity, the so-called C-star axiom. And it's a kind of miracle that such a simple axiom leads to a very rich and powerful theory. So in fact, the C-star algebra theory is much richer and much more powerful than, for example, the general theory of arbitrary Banach algebras. C-star algebras were first introduced in 1943 in a foundational paper by Gelfand and Nijmark. This paper was extremely important and very influential. Some people even say that this paper changed the face of modern analysis. So in some sense, it made the modern analysis much more algebraic than it was before. The original motivation for Gelfand and Nijmark was to apply C-star algebras to representation theory of groups. By the way, Gelfand often said that representation theory is all of mathematics. Nowadays, C-star algebras has the theory of C-star algebras has many applications, not only in representation theory, but also in many other fields of mathematics, such as, for example, operator theory, harmonic analysis, dynamics, algebraic topology, K-theory, index theory of differential operators, non-commutative geometry, and quantum group theory. Well, now let me say a few words about quantum groups. There is a well-known saying that a quantum group is neither quantum nor group. There is no general definition of a quantum group. And in fact, it is impossible to give such a definition because there are too many different objects which are called quantum groups. And what is common for all of them is the following informal way of constructing such objects. So we start with a group. G is a group. And well, what is a group? It can be an arbitrary group, just a group without any additional structure, or it can be an algebraic group, or a Lie group, or it can be a locally compact topological group. So we take our group, and then we construct a Hopf algebra-like object, A. The Hopf algebra-like object. Which is associated to our group G, and which normally contains all essential information, or maybe almost all essential information about the group. Usually this is an algebra equipped with some additional structure. In particular, it has so-called co-multiplication, which is a homomorphism delta from A to the tensor product, A tensor A. Here, the tensor product should be understood in a rather broad sense. So it can be either the algebraic tensor product, or the completion of the algebraic tensor product with respect to some norm, or even a bigger algebra, the so-called multiplier algebra. So finally, we take our algebra-like object A, and we deform it in some way. And what we get at the output is a quantum group. Again, here the word deformation should be understood in a broad sense. So it is not necessarily a formal deformation in the sense of Western-Haber. It can be, for example, another type of deformation, strict deformation quantization in the sense of Riffel, or some other procedure. But anyway, it's some kind of deformation of the original Hopf algebra constructed out of our group G. Here are some special cases of this procedure. For example, suppose that G is a semi-simple Lie group. So in this case, we can do the following. First, we take the Lie algebra of G. And we take the universal enveloping algebra, which has a natural structure of a Hopf algebra. In this case, there are some ways to quantize this object. And this quantization or deformation leads to so-called quantized enveloping algebras, denoted UQ of G or UH of G. They're a bit different, but they are closely related. So here Q is a number and H is a formal parameter. Such quantum groups, or more exactly quantized enveloping algebras, were introduced by Drinfeld and Jimbo independently. Around 1985 or 86. Another approach to quantum groups, which was discovered by Voronovich, again, independently of Drinfeld and Jimbo, looks as follows. We start with a compact group, G, compact group. And we take the algebra of continuous functions on G, which is, by the way, a commutative C-star algebra, which has some additional structure. In particular, it has a co-multiplication. Then we somehow deform or quantize this object. And what we get is a compact quantum group in the sense of Voronovich, denoted by CQ of G. So this is a non-commutative C-star algebra. Usually it is not commutative. And it is, well, in fact, there is another approach to the same class of objects, but in our course, I will concentrate on the approach developed by Voronovich. So this is what we are going to do. This is Voronovich's approach to quantum groups. These two approaches, I mean, the approach of Drinfeld and Jimbo and Voronovich's approach, they seem quite different from each other, but in fact they are closely related. Let me briefly explain the relation between these two approaches. For example, if we start with the quantized and developing algebra of SL2, UQ of SL2, this algebra has kind of Hopf dual, which is denoted like this, and is called the algebra of regular or polynomial functions on the quantum SL2 group. Algebras of this form were first systematically studied by Fadeev, Reshetikhin, and Takhtajan. This algebra has a natural involution, and when we equip it with the involution, the resulting algebra is usually denoted like this. So the notation is justified by the fact that SC2 is a compact, maximal compact subgroup of SL2. And after we take the C-star completion of this algebra, C-star completion, what we get is Voronovich's quantum SU2 group, CQ of SU2. In fact, there is a quantum, kind of quantum converse procedure, which enables us to recover the quantized and developing algebra of little SL2 out of Voronovich's quantum group CQ of SU2. But in general, there is no one-to-one correspondence between these two classes of objects. Okay, so this was an informal introduction. So now my goal today is to give you a brief survey of One Algebras. Survey of One Algebras. So most of these facts are traditionally included in courses of functional analysis. So mostly I'll omit the proofs of the results. We start with the following convention. All vector spaces and all algebras we are going to consider will be over the field of complex numbers. So everything will be over the complex numbers. By an algebra, I always mean an associative algebra over the complex numbers. That is, an associative ring A equipped with a vector space structure such that the multiplication on our algebra is bilinear over the complex numbers. So explicitly, this means that we have the following identity. You have two elements of A, little a and little b, and the complex number lambda, then the following equalities hold. Here, little a and little b are elements of our algebra, and lambda is a complex number. In general, our algebras are not assumed to have an identity. And an algebra with an identity is called unital algebra. A is unital if it has an identity element. If we have two algebras A and B, then a map phi from A to B is an algebra homomorphism. If it is a ring homomorphism, and if it is linear, a linear map over the complex numbers. If A and B are unital, then it is natural to consider those homomorphisms which take the identity to the identity. Such a homomorphism is called a unital homomorphism. So if A and B are unital, then we say that phi is unital if it takes the identity of A to the identity of B. Okay, now let's recall the definition of a normed algebra. By definition, a normed algebra is an algebra A equipped with a norm so it's an algebra and the norm space at the same time. And the norm is related with the multiplication by the following axiom. The norm of the product is less than or equal to the product of the norms. And in this case, we say that the norm is submultiplicative. If A is unital, we also require that the norm of the identity element equals 1. If A is unital, and of course, if A is non-zero. And finally, what is a Banach algebra? Well, the definition is very natural. A Banach algebra is a complete normed algebra. Complete in the usual sense that each Cauchy sequence converges. A short comment about the definition. So what is the role of this submultiplicativity condition? Well, this condition easily implies this simple exercise that the multiplication in each normed algebra is continuous. The multiplication is continuous. And in fact, the kind of converse is also true. More exactly, if we have an algebra equipped with a norm, and such that the multiplication is continuous, then we can always find an equivalent submultiplicative norm on the algebra. And moreover, if it is also unital, then this equivalent submultiplicative norm can be constructed in such a way that the norm of the identity element equals 1. This is a good exercise, by the way, to show that this is true. Okay. Let's now look at some examples of One algebras. First of all, we have a trivial example. The zero algebra and the field of complex numbers are, of course, One algebras. As for interesting examples, in fact, almost all concrete examples of One algebras can roughly be divided into three groups, namely the function algebras, operator algebras, and group algebras. Of course, these classes are not disjoint. For example, sometimes a group algebra can be represented as a function algebra, or a function algebra is an operator algebra in disguise. For our purposes, the most important class is the class of operator algebras. But function algebras and group algebras will also be quite important. The basic example of Banach function algebra is the following. Suppose that X is any set, and let's take the algebra of bounded functions on X, little than infinity of X. Well, of course, it's an algebra with respect to the pointwise product, and it has the canonical norm, the supremum norm. It's easy to see that this is Banach algebra. With respect to the supremum norm. Another example. Suppose now that X is a topological space. And we denote by CB of X the algebra of continuous bounded functions on X. The algebra of those functions which are continuous and bounded. It's a standard fact that this algebra, this is a closed subalgebra in little than infinity of X. It's a closed subalgebra. And it's immediate that the closed subalgebra of a Banach algebra is also a Banach algebra. This algebra CB of X contains an important subalgebra which consists of functions which vanish at infinity. So we give the following definition. If X is a topological space, then we say that a function f on X vanishes at infinity. If for each positive epsilon there exists a compact subset K of X such that f is less than epsilon outside K. Briefly, this condition is often written in the following way. Which is, of course, consistent with the traditional notation from calculus. So now our next example for Banach algebra is the algebra C0 of X, which consists of those continuous functions on X which vanish at infinity. It is already regularly seen that C0 of X is a subalgebra, a closed subalgebra, and moreover, a closed ideal in CB of X. So it is a Banach algebra. Observe that in general, this algebra is not unital. In fact, it's a good exercise to show that if X is Hausdorff, locally compact, and is not compact, then C0 of X is not unital. However, there is another important special case. If X is compact, then of course C0 of X equals CB of X, and they're equal to the algebra C of X of all continuous functions on X. And this algebra is unital. The next example is the Beagle infinity algebra. So suppose that we have a measure space, X mu is a measure space, and we consider the space Beagle infinity of X mu, which consists of essentially bounded measurable functions on X, or more exactly of equivalence classes of essentially bounded measurable functions. Essentially bounded means that the function is bounded on a set of full measure. And as usual, two functions are equivalent if they are equal almost everywhere. So this is known to be a Banach space with respect to the essential supremum norm. And of course, it's an algebra under pointwise multiplication. It's a simple exercise to show that the norm is submultiplicative, so it's a Banach algebra. Another example, and an exercise at the same time. Let's take the algebra Cn of AB of n times continuously differentiable functions on closed interval. I claim that this is a Banach algebra with respect to the following norm. The norm of f is given by the following formula. For each k from 0 to n, we first take the supremum norm of the kth derivative and divide it by k factorial. So this norm is submultiplicative, and the algebra is complete. So it's a Banach algebra. One more example of function Banach algebra, which is important for some problems of approximation theory and complex analysis. So suppose that K is a compact subset of the complex plane. We denote by A of K, script A of K, the algebra of those continuous functions on K, which are holomorphic on the interior of K. It's a simple exercise in complex analysis to show that this is a closed subalgebra in C of K. So it is a Banach algebra. An important special case is the case where K is the closed disk on the complex plane. So let's denote by bold D the closed disk of radius 1 centered at 0. Then the respective algebra, A of D, is one of the classical test examples in One algebra theory, and it is called the disk algebra. Okay, so all these examples are function algebras. Now let's look at a couple of examples of operator algebras. The simplest example and the most basic example of an operator algebra is the algebra of all bounded linear operators on the Banach space. So if E is a Banach space, then script B of E denotes the algebra of all bounded linear operators on E. And it is standard fact from function analysis that this is a Banach algebra. This algebra contains an important ideal, which consists of compact operators. So script K of E denotes the set of all compact linear operators. And again, it's a standard fact that K of E is a closed two-sided ideal in B of E. So it's a Banach algebra. And usually, if A is infinite dimensional, this algebra is not unital. Well, more examples of operator algebras will come later when we discuss C-star algebras and compact quantum groups. To complete our list of examples, let me give you one example of a group Banach algebra. In fact, if we have a locally compact topological group, then we construct a large family of different group algebras constructed out of the group. Now I'll give only the very special simplest example of this group algebra, which corresponds to the situation where the group is discrete. So suppose that we have a group G. So if you like, we may consider it as a topological group with a discrete topology. And we denote by little L1 of G the usual little L1 space, which consists of those functions on G, which satisfy the following conditions. So the following series converges. Well, this is known to be Banach space with respect to this L1 norm. But it is also Banach algebra. The product in the multiplication in this algebra is called convolution. And the convolution is defined as follows. If we have two L1 functions, f and g, then their convolution, f star g, is also a function on g, given by the following formula. Sum over all elements y in the group. It's a simple exercise to show that the series indeed converges, and the resulting function is also an element of the little L1 space. And this operation makes little L1 of G into One algebra with convolution product. By the way, this algebra contains the algebraic group algebra of G, which is included, which is embedded into L1 of G, and which consists of all finitely supported functions on G with convolution product. This is the algebraic group algebra. Okay, so these are our basic examples. More examples will come later. And now let me briefly recall some basic facts from the spectral theory in One Algebras, which we will need later. So we start with the unital algebra A. At this point, it is just a unital algebra. It is not necessarily a One algebra. And we denote by A cross the set of all invertible elements in A. This is a so-called multiplicative group of A. Now the definition of spectrum of any element in our algebra looks as follows. The spectrum of an element little a in our algebra, spectrum of little a, is a subset of the complex plane, denoted by sigma of a. It consists of all complex numbers lambda, such that a minus lambda is not invertible. Well, let's look at some concrete examples. Well, for example, if A is the field of complex numbers, then the spectrum of each element lambda is lambda itself. So it contains only one point. Another example, which comes from finite dimensional linear algebra, if A is the algebra of linear operators on a finite dimensional vector space, let's denote this algebra simply by L of E, where E is a finite dimensional vector space. Then the spectrum of each operator, each linear operator on E, is nothing but the set of all eigenvalues of T. Of course, it's essential here that the space is finite dimensional. So if E is not finite dimensional, then all eigenvalues are contained in the spectrum, but in general, the spectrum can be much bigger than the set of all eigenvalues. Now let's look at some function algebras. Suppose that X is any set, and A is the algebra of all complex valued functions on X. Then it's easy to see that the spectrum of a function, f, is nothing but f of x, the range of this function. This is true simply because the function is invertible, if and only if it is non-vanishing. And the same is true for a number of other important function algebras. For example, the same is true for the algebra of continuous functions on the topological space, essentially for the same reason. And for example, for the algebra of smooth functions on the manifold. And for many other algebras, for algebras of holomorphic functions, for example, the same result is true. But there are examples of function algebras for which this formula fails. For example, if we take again an arbitrary set X and take the algebra of bounded functions, little infinity of X, then it is easy to see that for each function f in this algebra, the spectrum of f is the closure of f of x. And this follows from the fact that a function in this algebra is an invertible element if it is bounded away from 0. So if 0 is not in the closure of f of x. Well, our next example is the Beagle infinity algebra. Before we discuss it, let's give the following definition. Suppose that we have a measure space, X mu, measure space, and a complex function, measurable function f on X. We say that complex number lambda belongs to the essential range of f, or sometimes we say that it is an essential value of f, if for each neighborhood u of lambda, the pre-image of u under f has positive measure. In general, the essential range of f is not necessarily contained in f of x, and f of x is not necessarily contained in the essential range. However, if, for example, x is a compact topological space, and mu is a good Borel regular measure, such that the measure of each non-empty open set is strictly positive, then it's rather easy to show that for each continuous function on x, the essential range of f equals f of x. Now, the spectrum of any element in the Beagle infinity algebra can be described as follows. So if A is the Beagle infinity algebra, then for each element f in A, the spectrum of f is nothing but the essential range of f. This is a simple exercise. Okay, let's now look at some simple algebraic properties of the spectrum. First of all, we have the following easy but useful proposition. Suppose we have two unital algebras, A and B, and suppose that phi is a unital homomorphism from A to B. Then we have the following results. First of all, phi always takes invertibles to invertibles. Each invertible element of A goes to an invertible element of B. This readily implies that for each element little a of the algebra A, the spectrum of its image, phi of A, is contained in the spectrum of A. And sometimes some important homomorphisms preserve the spectrum in the sense that these two sets are the same. And this happens if and only if phi takes non-invertibles to non-invertibles. So phi takes non-invertibles to non-invertibles if and only if it preserves the spectrum. That is, for each A, we have the following equality. An important special case of this result is the following corollary. Suppose that A is a unital algebra. And suppose that B is subalgebra of A, such that the identity of A belongs to B, so that they have the same identity. In this case, for each element little b of the smaller algebra, the spectrum of B calculated with respect to A is contained in the spectrum of the same element calculated with respect to B. So we have such an inclusion. This is a special case of the previous proposition if we apply it to the inclusion of B into A. And in some cases, these two spectra are the same, and there is a special name for this situation. We say that B is spectrally invariant. Spectrally invariant in A if for each element little b in the subalgebra, the spectrum of B calculated with respect to A equals the spectrum of B calculated with respect to the subalgebra B. And it follows from our previous proposition that this is equivalent to the following equality. Which means that each element of A, each element of B, which is invertible in A, is actually invertible in B. Here are some examples of spectral invariant subalgebras. For example, for each topological space, we have already seen that C of X, the algebra of continuous functions, is spectrally invariant in the algebra of all functions on X. On the other hand, if we take an arbitrary set big X and consider the algebra of bounded functions on X, little infinity of X, then this algebra is not, in general, it is not spectrally invariant in the algebra of all functions on X. In fact, it is not spectrally invariant for each infinite set X. Well, indeed, we have already seen that the spectrum of a bounded function is the closure of f of x. And the spectrum of a function considered as an element of the algebra of all functions is just f of x. So since x is infinite, it is very easy to construct a function, a bounded function, f, whose range is not bounded. Whose range is not closed. Whose range is not closed. So the algebra is not spectrally invariant. Another example is A of k. So if k is any compact subset of the complex plane, also let's recall that A of k consists of those continuous functions which are holomorphic on the interior of k. And this is to see that this subalgebra in C of k is spectrally invariant. And another important example is the algebra of bounded operators on a Banach space. So B of E, the algebra of all bounded operators on a Banach space, is contained in the algebra of all operators on E, which we denoted by L of E. And this algebra is spectrally invariant for each Banach space E. And this statement is actually an equivalent form of Banach's inverse mapping theorem, which tells us that if we have a bijective bounded linear operator on E, then the inverse operator is also bounded. And this means precisely that this subalgebra is spectrally invariant. Another useful algebraic property of the spectrum is the following spectral mapping theorem, the polynomial spectral mapping theorem. So suppose we have a unital algebra A, unital algebra, an element relay of A, and a complex polynomial f of one variable. Then we can consider the element f of A. This is a well-defined element in our algebra. And we can calculate the spectrum of this element. And in this case, we have the following simple and easy to remember formula. The spectrum of f of A equals f of sigma of A. That is the image of the spectrum under F. And this formula holds almost everywhere, except for the trivial case in which it fails. So this formula holds unless the spectrum of A is empty and F is a constant. Because in this case, well, the spectrum of it is empty, so the right-hand side of our formula is also empty. But the left-hand side is the spectrum of a constant, which is not empty. But in all other cases, the formula is true and is very useful. In fact, this formula has many analytic counterparts. For example, if A is a Banach algebra, then this expression f of A makes sense not only for polynomials, but also for each holomorphic function defined in the neighborhood of the spectrum. And the formula is still true. And we will also see soon that if A is a unital C-star algebra, and the element Lily is normal, then the expression f of A makes sense for each continuous function on the spectrum. And the spectral mapping formula is still true. Another closely related result is the following proposition, which gives us a formula for the spectrum of the inverse element. So if A is a unital algebra, and little a is an invertible element of A, then the spectrum of A inverse is given by the following formula. Here lambda runs over the spectrum of A. In fact, both this result and the polynomial spectral mapping theorem are special cases of a more general rational spectral mapping theorem. which states that the same formula, sigma of f of a equals f of sigma of a, is true for each rational function defined on the spectrum. So that is for each rational function whose poles are outside the spectrum. In fact, this is a good exercise to extend the polynomial spectral mapping theorem to rational functions. Okay, so all these results are, of course, purely algebraic. And now let's come back to functional analysis and recall some basic facts about the spectrum of an element of a Banach algebra. The most important results about the spectrum are due to Griffand, and they tell us that the spectrum of any element of a Banach algebra is compact and non-empty. And this essentially follows from the following result, which describes some important properties of the multiplicative group of a Banach algebra. So suppose that A is a unital Banach algebra. Then we have the following results. First of all, if little a is an element in our algebra, such that the norm of a is less than 1, then the element 1 minus a is invertible. And there is the following explicit formula for the inverse of this element. The second result is actually a corollary of the first result, and it tells us that the multiplicative group of A is open in A, is an open subset of A. And finally, the inversion map, the map from A cross to itself, which takes each element little a to little a inverse, is continuous. So these are the basic properties of the multiplicative group of a Banach algebra. By the way, there is a nice corollary of this theorem. So we have the following definition. Suppose that A is any algebra. As usual, over the complex numbers. Then by definition, a character of A is an algebra homomorphism from A to the complex numbers. By the way, it's a simple exercise, or rather an observation, that if A is unital, and say chi is a non-zero character of A, then chi is unital. Well, essentially, this follows from the fact that if chi is non-zero, then it is surjective. And a surjective homomorphism between unital algebras is necessarily unital. So we have the following useful corollary of the previous theorem. Suppose that A is a unital Banach algebra, and chi is a character of A. Then chi is automatically continuous. Chi is continuous. And the norm of chi is less than or equal to 1. Well, let's prove this result. This is very easy and very nice in my view. First of all, without loss of generality, we may assume that chi is unital. Because of the previous exercise. If it is 0, then there is nothing to prove. And if it is not 0, then it is unital. So suppose now that chi is either unbounded or the norm of chi is bigger than 1. So if norm of chi is bigger than 1, or if chi is discontinuous or equivalently unbounded, then we can always find an element. There's an element, say B, in our algebra, such that the modulus of chi of B is strictly bigger than the norm of B. And so by multiplying B by a suitable number, we find another element, little a, such that the norm of a is less than 1, and such that chi of a equals 1. Actually, a is nothing but b divided by chi of b. Well, since the norm of a is smaller than 1, we conclude so our previous theorem, the first part of the previous theorem, implies that 1 minus a is invertible. One minus a is invertible, and chi is unital, and the unital homomorphism take invertibles to invertibles. So chi of 1 minus a is not 0. But chi is unital, so chi of 1 minus a is 1 minus chi of a. And this is 0 because chi of a equals 1. And this is a contradiction. This result is an illustration of a very special phenomenon, which is called automatic continuity. So it turns out that in many important cases, the continuity of a certain map between One algebras automatically follows from its algebraic properties. And we will meet other instances of this phenomenon fairly soon. Well, now let's come back to the spectrum. We have the following fundamental result due to Gelfand. Suppose that A is a unital One algebra. And little a is an element of our algebra. Then we have the following statements. First of all, for each element little lambda in the spectrum, the absolute value of lambda is less than or equal to the norm of A. Second, the spectrum of A is compact. And finally, if our algebra is not 0, then the spectrum of A is non-empty. In fact, the first and the second parts of this theorem are rather easy. Namely, part 1 follows from our previous result on the multiplicative group. So this implies that the absolute value of each element in the spectrum is bounded by the norm of A. And the second statement of this theorem implies that the spectrum is closed. So the spectrum is both closed and bounded, so it is compact. So this gives us the second part of Gelfand's theorem. The third part is slightly more involved. It is based on some on the so-called resolvent function of our element. So the idea is to take a bounded functional f on A and consider the following function. If the spectrum is empty, then this function is defined everywhere on the complex plane, and it can be shown that this function is bounded and holomorphic. And the bounded holomorphic function is a constant by Liouville's theorem. So this is the basic idea of the proof. As a corollary of Gelfand's theorem, we obtain the following nice result. This is the so-called Gelfand-Mazur theorem. Suppose that A is a Banach division algebra. That is a unital One algebra different from 0, such that each non-zero element is invertible. Sometimes such algebras are called skew fields. So it is like a field, but it's not necessarily commutative. So the Gelfand-Mazur theorem states that this algebra is necessarily isomorphic to the complex numbers. And the proof is very easy. It's just a line. If take an arbitrary element in our algebra, then we already know that the spectrum is non-empty. So we can always find a complex number lambda such that A minus lambda is not invertible. But since A is a division algebra, this means that this element is 0. That is, A equals lambda 1. So actually, A is spanned by the identity element. By the way, the Gelfand-Mazur theorem has also an analog for real numbers. The real version of the Gelfand-Mazur theorem states that if A is a Banach division algebra over the real numbers, then it is isomorphic either to the real numbers, or to the complex numbers, or to the quaternions. So there are only 3 possibilities. And this result extends the classical Frobenius theorem, which states the same for finite dimensional algebras. By the way, the Gelfand-Mazur theorem has a rather remarkable history. It was proved originally by Mazur at the end of the 1930s, and it was proved over the real numbers, which is much more difficult, by the way, than the complex version of the Gelfand-Mazur theorem. But for some strange reason, Mazur submitted his paper to the French journal Compte Rendu, which is known to publish only brief communications. So quickly, Mazur received a reply from the editor, which said that, well, your paper is interesting, but it is too lengthy, too long for our journal. So you have to reduce it somehow. So Mazur just, he has thrown away all the proofs. And the paper was published, but there were no proofs. And a few years later, Gelfand independently obtained the same result, but only for the field of complex numbers. So the first published proof is due to Gelfand, but it works only for the field of complex numbers. And Mazur's result, the real version of the Gelfand-Mazur theorem, the proof was published only in 1960 in Ricard's book on Banach algebras. So this is the history of this result. Well, also I wanted to recall you some basic facts about spectral radius in One algebras, but I see that it's time to finish. So that's all for today. And at the next lecture, we recall some facts on the spectral radius in One algebras, and then begin to discuss Gelfand's theory of commutative One algebras. Thank you.